After studying this module, you shall be able to know number 1 about uniform distribution, its expected value and variance. Number 2 about normal distribution, its properties, expected value, variance and how to represent normal probability distribution on bell-shaped Gaussian curve. Number 3 about exponential distribution and its properties. In this module, we shall learn about continuous probability distribution and its various types. Continuous probability distribution can be categorized into different probability distributions according to its theoretical approach. In this module, we would be focusing on the following. Number 1, normal distribution. Number 2, uniform distribution. And number 3, exponential distribution. The graphs of the above distributions are symmetric and are useful in predicting the likelihood of an event within a certain range of values. All the above distributions are parts of theoretical continuous distributions. We will start with the concepts of continuous probability distribution and then talk about the 3 theoretical distributions mentioned above. First, we will discuss probability density function of continuous probability distribution. If x is a continuous random variable, then a function fx describing the probabilities of x is called probability distribution function of x or probability density function. The following are the properties of probability density function of x. Fx greater than equal to 0 and integral minus infinity to plus infinity f of x dx is equal to 1. The first of these two conditions states that for fx to be probability density, it must have non-negative values throughout the range of x. The second condition requires that the sum of the probability elements fx over the entire range of x is 1. Also, the probability of x falling within any two values x1 and x2 is probability of x1 less than x less than x2 is equal to integral x1 to x2 f of x dx. Since fx is a probability density function, probability of x1 less than x less than x2 is a proportion area under a smooth probability curve. Let's now move on to distribution function under continuous probability distribution. The distribution function denoted by fx is the probability that a random variable with the probability density fx takes on a value less than or equal to x. Thus, for any value x, f of x is equal to probability of capital X less than equal to small x is the area under the probability density function over the interval minus infinity to x. In the usual calculus notation for the integral, f of x is equal to minus infinity to x f of t dt. According to the fundamental theorem of calculus, it follows that fx is the derivative of capital Fx with respect to x whenever this derivative exists. Also, another consequence of this theorem is that the probability that a random variable will take on a value in the interval from a to b is f of b minus f of a. Moving on to the uniform distribution. If x is a continuous random variable belonging to the interval alpha beta, then it is said to follow uniform distribution if its probability density function is f of x is equal to f of x alpha comma beta is equal to 1 upon beta minus alpha for all x belonging to the interval alpha beta. The graph of uniform probability density function is shown in the figure. In uniform distribution, the probabilities of all the outcomes are the same. Also, the total area within the rectangle is equal to 1. The probability at any point x within the interval alpha beta is equal to 0. Also, the probability that a single observation x will fall in an interval AB entirely contained in the interval alpha beta is given by P of A less than equal to x less than equal to b is equal to integral a to b f of x dx is equal to capital FB minus capital FA, which is equal to b minus a upon beta minus alpha. The uniform distribution is biparametric and its parameters are alpha and beta. The mean and variance of uniform distribution is as shown. E of x is equal to alpha plus beta upon 2. Variance of x is equal to beta minus alpha whole square upon 12. The above mean is derived as follows. E of x is equal to integral alpha to beta x fx dx, which is equal to integral alpha to beta x into 1 upon beta minus alpha dx, which is further equal to 1 upon beta minus alpha into x square upon 2 x varying from alpha to beta. This is equal to 1 upon 2 into beta minus alpha multiplied by beta square minus alpha square, which is equal to beta minus alpha into beta plus alpha upon 2 into beta minus alpha equal to alpha plus beta upon 2. The cumulative distribution fx of the uniform distribution is fx is equal to 0 when x is less than alpha is equal to x minus alpha upon beta minus alpha when alpha is less than equal to x is less than beta, it is equal to 1 when x is greater than beta. Let us understand the distribution function of uniform distribution graphically. Over here, starting from alpha, the value of fx is 0. As the value of x increases, the value of fx also increases continuously with its slope equal to 1 upon beta minus alpha and will reach 1 maximum when x is equal to beta. At x equal to beta, there is a kink, and at x greater than beta, the slope of fx is equal to 0. Let us understand it with the help of an example. At a certain bus stop, a bus arrives at every 2 minutes. If a passenger reaches the bus stop when there is no waiting bus, what is the probability that he will have to wait for 45 seconds for the next train? What is the mean and variance of the waiting time? Minimum waiting time alpha is equal to 0 minutes. Maximum waiting time beta is equal to 2 minutes. Let x be the random variable waiting time. Evidently, x may take any value within the interval 0, 2. Also, assuming randomness of arrival, we can expect x to be distributed uniformly over that interval. This means that over the range x, fx will be a constant and follow a uniform distribution probability density function defined as f of x is equal to 1 upon beta minus alpha for 0 less than x less than equal to 2, which is equal to 1 upon 2 minus 0, which is further equal to 1 upon 2. Diagrammatically, this distribution appears in the figure. Now 45 seconds is equal to 45 upon 60 is equal to 0.75 minutes. Thus, in the present case, we may evaluate the required probability as P of x less than equal to 0.75 is equal to 0.75 upon 2 is equal to 0.375. In the diagram, the probability is represented by the hatched area. The graph of the cumulative distribution function appears in the figure. Fx is equal to 0 for x less than 0. It is equal to x minus alpha upon 2 when 0 is less than equal to x is less than 2, and it is equal to 1 when x is greater than 2. In the figure, fx will increase continuously with slope equal to 1 upon beta minus alpha, which is equal to 1 by 2, and will be equal to 1 when x is equal to 2. Moving on to the normal distribution. If x is a continuous random variable, then it is said to follow a normal distribution when its probability density function is fx is equal to 1 upon sigma into under root 2 pi whole multiplied by e to the power minus 1 by 2 into x minus mu upon sigma whole square, where minus infinity is less than x is less than infinity, where mu is the expected value of the distribution and sigma is the standard deviation of x in the population, and pi is equal to 3.14159 and e is equal to 2.71828 are mathematical constants. The normal distribution is biparametric, having parameters mean, mu, and variance sigma square, and is symbolically written as x is equivalent to n of mu comma sigma square. Let us now look at the properties of normal distribution. First, fx lies between 0 and 1, that is 0 is less than equal to fx is less than equal to 1. Second, minus infinity to infinity f of x dx is equal to 1, that is the total area under the normal distribution curve is equal to unity. Since the curve is symmetric, the area in each tail equals 0.5. The next property is that the normal distribution is represented by a symmetrical bell-shaped curve whose tails extend infinitely in both directions. That is, it is asymptotic in both directions to the x-axis. Thus, the normal density function fx is everywhere positive. This is explained through figure. The fifth property is that due to being symmetric, the mean, median and mode of a normal distribution coincide. Mu is equal to me is equal to mo. This is illustrated in figure as well. Moving on to the sixth property, we have for a particular normal distribution with given mu and sigma, the probability of x falling within x1 and x2 is the integral of fx between x1 and x2. That is, probability of x1 less than x less than x2 is equal to integral x1 to x2 1 upon square root of 2 pi sigma square multiplied by e to the power minus 1 by 2 multiplied by x minus mu upon sigma whole square dx. The shape of the normal distribution curve depends upon its parameters mu and sigma square. In other words, every normal distribution will have a different shape with different parameters, where mu indicates the central value of the distribution and sigma the dispersion about mean. Thus, if mu will change, the curve will shift only along the x-axis without any change in its shape, and a change in sigma only will change the spread of the curve with no shift. An increase in sigma will make the curve more flatter, whereas a decrease in sigma will make the curve steeper. In figure, mu2 is greater than mu1 and sigma 1 is greater than sigma 2. The last property of normal distribution states if the normal variable x is transformed to a new variable z is equal to x minus mu upon sigma called the standard variable, then the normal distribution changes to the form f of z is equal to 1 upon under root 2 pi multiplied by e to the power minus half z square, where minus infinity is less than z is less than plus infinity. This is called standard normal distribution whose mean and variance are always 0 and 1 respectively. That is, z is equivalent to n of 0, 1. This distribution is unique since it does not depend on the values of the parameters mu and sigma. Let us now understand why do we convert normal distributions into one standard form. We convert because there exists an infinite number of possible normal distributions, each with its own mean and standard deviation, and it becomes a very difficult task to examine such a large number of possibilities. This can be explained with the help of the following example. Let the random variable x be the daily salary of employees in a particular company. Then first employee follows x equivalent to n of 56, 2. Second employee follows x equivalent to n of 56, 4. Third employee follows x equivalent to n, 68, 2. Now plotting the normal distribution of salaries of all the three employees, we get the figure as shown. Now to find the probability for a particular interval, we would require a probability table for every particular combination of parameters. But after converting these three different normal distributions into a standard normal deviation form, we get figure 7.8, where n1 is equivalent to 56, 2, n3 is equivalent to 68, 2 overlap each other since sigma is same, and n2 is equivalent to 56, 4 having greater sigma is more flatter and can be plotted on the same x-axis. In figure 1, sigma is equal to plus minus 2x, and therefore 2 sigma is equal to plus minus 4x. After the conversion process, the mean of standard normal distribution is 0 and the standard deviation is 1 always. Regardless of what the mean and standard deviations was measured in the original units of the normal distributions, that is, z is equivalent to n 0, 1 always. Thus to find the probability that x falls within the interval x1 and x2, we first need to convert the normal variable into standard normal variable and then find the probability that the standardized normal variable z falls within the range z1 and z2, where z1 is equal to x1 minus mu upon sigma and z2 is equal to x2 minus mu upon sigma. It is explained through the figure. Let us understand it with the help of an example. Costa Coffee morning customer load follows a normal distribution with mean 45 and standard deviation 8. Determine the probability that the number of customers tomorrow will be less than 42. We first convert the raw score to a z-score. Given mu is equal to 45 and sigma is equal to 8, we get z is equal to 42 minus 45 upon 8, which is equal to minus 0.375. Next, we use the z value table to find the probability, which amounts to 0.352, which we have rounded the raw score to minus 0.38. This is also illustrated in the figure. We can conclude that probability of x less than 42 is equal to 0.352. That is, there is about a 35.2% chance that there will be fewer than 42 customers tomorrow. Further, moving on to why is the normal distribution useful? Many things actually are normally distributed or very close to it. For example, height and intelligence are approximately normally distributed. Measurement errors also often have a normal distribution. The normal distribution is easy to work with mathematically. In many practical cases, the methods developed using normal theory work quite well when the distribution is not normal. There is a very strong connection between the size of a sample n and the extent to which a sampling distribution approaches the normal form. Many sampling distributions based on large n can be approximated by the normal distribution, even though the population distribution itself is definitely not normal. Also, the normal distribution can be used to approximate the binomial distribution when n is large and p, the probability of success, is close to 0.5. Further, moving on to exponential distribution. The exponential distribution is the probability distribution that describes the length of the time interval between successive events occurring in a Poisson process. The formula for the probability density function of the exponential distribution with parameter lambda is f of x comma lambda is equal to lambda e to the power minus lambda x when x is greater than equal to 0 and is equal to 0 when x is less than 0. The figure is the plot of the exponential probability density function. Let us now look at the characteristics of the exponential distribution. The exponential distribution has one parameter equal to lambda. Also, in this distribution, both mean and standard deviation are equal to 1 upon lambda. Another important feature of exponential distribution is that it is always positively skewed with its value always equal to 2. Also, the exponential distribution is leptokurtic and the coefficient of kurtosis is always equal to 6. This distribution is properly normalized. The formula for the cumulative distribution function of the exponential distribution is f of x comma lambda equal to 1 minus e to the power minus lambda x when x is greater than equal to 0 and this is equal to 0 when x is less than 0. The figure shows the plot of the exponential cumulative distribution function. Let us now understand the application of exponential distribution. First, the family of exponential distributions provides probability models that are very widely used in engineering and science disciplines. Second, the exponential distribution is closely related to Poisson process and is frequently used as a model for the distribution of times between the occurrence of successive events. If the number of occurrences in Poisson is distributed, the lapse of time between occurrences will be exponentially distributed. Given a Poisson distribution with parameter alpha t, where alpha is equal to the expected number of events occurring in 1 unit of time and t is equal to time interval of length, and the number of occurrences in overlapping intervals are independent of one another, then the distribution of elapsed time between the occurrences of two successive events is exponential with parameter lambda equal to alpha. Third, exponential distribution can model the distribution of component lifetime. This is because of the reason that exponential distribution exhibits memoryless property, which implies that the distribution of additional lifetime is exactly the same as the original distribution of lifetime. That is, the distribution of the remaining lifetime is independent of current age. Let us understand the exponential function with the help of an example. Accidents occur with a Poisson distribution at an average of 4 per week, that is lambda equal to 4. Calculate the probability of less than 6 accidents in 1 week. What is the probability that at least 4 weeks will elapse between accidents? It is clear that the first part involves Poisson distribution, where we are talking about the probability of accidents, which is a discrete variable, and the second part involves exponential distribution, which we are talking about lapse time, which is a continuous variable. Thus, Poisson p of x less than 6 is equal to p of 6, 4, which is equal to 0.785. Exponential p of time between occurrences of accidents greater than 4 is equal to integral 4 to 8 lambda e minus lambda t dt, which is equal to e minus lambda t, t varying from 4 to infinity, which is further equal to e to the power minus 16. Let us now summarize what we have learned in this module. In a uniform distribution, all the values of x within its interval are equally likely. The normal curve is also referred to as the normal curve of errors. This is because whenever x is the sum of true value plus a very large number of small independent errors, each equally likely to be plus or minus, x will be distributed in the normal distribution. The exponential distribution describes waiting time between Poisson's occurrences. The maximum value of the cumulative distribution is 1, and after that the slope of cumulative distribution is always 0, that is, within increase in the value of x there will be no change in the value of the distribution function.